Hi, everyone. So what happens if two events are not mutually exclusive? What if they could happen simultaneously on the same trial? So for example, let's say that we're going to roll one standard six-sided die. What's the probability that the die will come up even, event A, or higher than a 2, event B? Let's start by using the brute force method. Let's find the number of ELOs for which A or B occurs, and then divide by n, or 6. I'm going to go up back to our rectangular array here. All right, again, A is the event even, B is the event higher than 2. One by one, let's go through these ELOs, these equally likely outcomes. If we roll a 1, does either event occur? Well, 1 is not even, 1 is not higher than 2, so the answer is no. We cross out the 1. What about 2? Well, 2 is an even number, but it's not higher than 2. 2 does satisfy A, but not B. What about 3? 3 is not even, but it is higher than 2. So for 3, event B occurs. What about 4? Now for 4, 4 is an even number, so event A occurs. But 4 is also higher than 2, so event B also occurs. Right off the bat, we realize that A and B are not mutually exclusive because we have at least one outcome for which both events occur. What about 5? 5 is not even, but it is higher than 2. Event B occurs. What about 6? 6 is even, and 6 is higher than 2. Okay, so for how many of these die rolls do we get A or B occurring? Well, neither occurs if a 1 is rolled, but if a 2 is rolled, if a 2 is rolled, if a 3 is rolled, if a 4 is rolled, if a 5 is rolled, if a 6 is rolled, then A or B, or both, will be occurring. So for 5 of these 6 ELOs, A or B will occur, which means that the probability of A or B occurring is 5 over 6, 5, 6. Now, what if we consider the probability of A and the probability of B? What if we had used our old school formula for that? What if we had treated them as Mees, mutually exclusive events? Well, the probability of A occurring would have been 3, 6, or 1/2, the probability of an even number, plus the probability of getting a number higher than 2 would have been 4 over 6, or 2/3. It turns out to be more convenient to deal with 6 anyway. But wait a minute, 3, 6 plus 4, 6 is 7, 6. I know immediately that I got the wrong answer. Why? Well, for one thing, this is bigger than 1. There's no way that this can be a probability. I know I messed up somewhere. And also, there's a more subtle problem. Why is this wrong? Because this ends up double counting the 4 and the 6 as outcomes. We're double counting the 4 outcome and the 6 outcome. So we have to adjust for that if you're going to use a formula. So how do you adjust for that? Again, notice that A and B, these two events, are not Mees. They're not mutually exclusive events because both events could happen at the same time on the same trial. Namely, if you get a 4 or if you get a 6, then both of these events will be occurring. And the key thing to remember is that you should not double count the equally likely outcomes. Do not double count the 4 and the 6. So here's the general addition rule. In the case where A and B could be mutually exclusive or not, Mees or not. The probability of A or B equals the probability of A plus the probability of B, and then we need this extra term for non-Mees. If you don't have mutually exclusive events, you need to subtract the probability of A and B occurring. This is referred to as the intersection of A and B, or more informally, the overlap of A and B. You subtract the probability of the intersection of the overlap. That's where the 4 and the 6 lie. So the probability of getting an even number or a number higher than 2 is the probability of an even number plus the probability of getting a number higher than 2 minus the probability of both happening. The probability of A happening, the probability of getting an even number, was 3/6, or 1/2. The probability of getting a number higher than 2, the probability of B, was 4/6. We did this before. Now, 3/6 plus 4/6 is 7/6. But the thing is, we also have to subtract the probability of the intersection or overlap. For how many of the ELOs do both occur? For 2. The 4 put this in orange. I'll put this in orange. Oops. So orange, probably of both. All right. In orange, here's the overlap. The 4 and the 6, they represent the overlap. What's the probability of getting something in the overlap? A 4 or a 6? That's 2/6. So we have to take the 7/6 here and subtract off 2/6, and then we get 5/6. That should sound familiar. That's what we got when we did it the brute force way. 5/6. 5/6 is correct. So in general, again, if A and B are events that are either mutually exclusive or not, the probability of A or B is the probability of A plus the probability of B minus the probability of both happening, P of A and B. Now, the Venn diagram can help out here, right? Because here's the deal. If you're adding P of A and P of B, the problem is that if they're overlapping, you're double counting this intersection or overlap, A and B. So in order to adjust for that, you have to subtract off the intersection piece once. You have to subtract off one of the colors, and then the other color still remains. We do want one of the colors to remain. It has to be counted, but only once, not twice. By the way, if you want to relate these to the ELOs, so an even number would be a 2, a 4, or a 6. I have to write tiny 4 and tiny 6 here. An even number would be 2, 4, 6. Okay. A number higher than 2, that would be 3, also 4. I'll circle the 4 in purple. Also 5, and also 6. I'll circle the 6 in purple. All right. So P of A plus P of B, but since we don't want to double count the red and circled items, we subtract off the probability of, say, one of the colors here. Okay. And that helps to adjust for the double counting. So again, a key theme: avoid double counting. That was up here. You have to avoid double counting. Do not double count. Now you might be asking, well, how is it that this formula applies even in the event of mutually exclusive events? Well, I'll show you the picture. So here's the picture of mutually exclusive events. Why is this formula still applicable? Well, the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B happening. But wait a minute. If you have Mees, if you have mutually exclusive events, what's the probability of both happening? That, in the case of Mees, is going to be 0. Because there is no intersection or overlap in the case of Mees. There are no outcomes for which both will occur. So the general addition rule is general because it applies to Mees or non-Mees. Because even if you have Mees, mutually exclusive events, that just means that this term is 0. It's still correct, though, the formula. All right, next up. Oh, first of all, as a challenge to you, this is not homework, but what if you had events A, B, and C, which might not be mutually exclusive? It's a much more complicated formula. Here's a hint. This could represent A, this could represent B, and this could represent C. You have the potential for double counting and also triple counting. This is a much more complicated formula. Don't freak out about it, but that's a challenge to you. Next up, we're going to talk about tables, how to find such probabilities using tables.